Jonah Myerberg, the co-founder and CTO of Desktop Metal. So glad to have you with us today, all the way from Boston, Massachusetts. Is that right?
That's right. It's a pleasure to be here.
Yeah. So glad to have you. So we get to get into kind of all things additive manufacturing, 3D printing, and Formula One racing today, which is exciting. Not a lot of topics that we've gotten to hit previously, so that's fun for the podcast. So why don't you just kick it off and tell me a little bit about who you are and what you're doing at Desktop Metal right now?
Great. Yeah. So my name is Jonah Myerberg, as you said. I'm a mechanical engineer. I studied mechanical engineering at Lehigh University and then at Johns Hopkins University, and started my career at Black & Decker designing power tools, and then moved up to Boston taking a job with Bose to design speakers and amplifiers with them.
That's pretty cool.
Yeah, and then got pulled into the battery industry through Black & Decker because Black & Decker is a company that probably tests different battery chemistries more than any other company in the world. It has to do with their power tools and their cordless lines of tools, and they want to be at the cutting edge of battery technology. And so my colleagues at Black & Decker brought me back into batteries when they discovered a new chemistry of battery being developed out of MIT up in Boston. And so I joined the battery world. And then after that, one of my colleagues in the battery world and I started a 3D printing company called Desktop Metal. And we started it to bring metal 3D printing to the engineer unlike it had ever been before, because 3D printing was beginning to take off and additive manufacturing promised a new way to manufacture parts. And so in 2015, we started Desktop Metal. And took it public in 2020, and then recently sold it to a company called Arc Impact. Right now we are a fully vertically integrated additive manufacturing company for metal alloys that works with our customers to bring them raw materials, printers, and the processes that they need to 3D print metal parts for all different types of industries.
Yeah. Wow. You hit on so many different things. Like, your background alone is so crazy that you've gone through a lot of different industries, it seems, all with your mechanical engineering background. But even just the battery field, I don't think I would have even known that was its own, separate industry in and of itself. So that's really interesting. Let's kind of dig into that a little bit. So you said you went to Lehigh University first, and then you went on to go to Johns Hopkins University. Is that correct?
That's right.
Okay. And you studied mechanical engineering at both those schools?
That's right.
Okay. And what was your role following your college experience? What were you doing?
Yeah. So I took a job with Black & Decker because it was really, as a mechanical engineer, it was really attractive to design power tools. I knew nothing about power tools. I wasn't.
Neither do I.
I was not one of those kids who, used a lot of power tools growing up. I was very interested in cars and in airplanes. And when I interviewed with Black & Decker, it became very apparent that the gears and the transmissions and the motors were exactly what I was looking for.
Yeah.
So I started developing woodworking tools with the DeWalt brand. So DeWalt was a brand owned by Black & Decker, still is.
Okay.
Since then, Stanley has purchased Black & Decker, and now it's a Stanley, Black & Decker, and a number of other brands. But my role was to develop new power tools, and the way that Black & Decker did that is that they sent their engineers out into the field for 6 months to work with the professionals who were using their power tools. So in my case, it was DeWalt power tools. Specifically, it was in Las Vegas, where they were building casinos and track homes. And so I lived in Las Vegas for 6 months, essentially working with the crews that were building the casinos back in the late 90s.
Okay.
And these
So you're working like with these construction workers that are building all of these different casinos.
Yes, exactly.
Okay.
I had a yellow truck full of power tools, and I would drive around to job sites and loan out power tools, talk to them about what they liked, what they didn't like.
Just like getting their feedback.
Totally, just getting their feedback. More of a marketing and research position. So not really trying to sell them on anything, but trying to understand what they liked about
Like
our
what
line.
they needed, what they wanted to see.
That's right, and also competitive tools, what they liked about other brands, and then what they would like to see in the future.
Okay, interested. I just don't think I would have ever even seen that connection between getting into batteries specifically and power tools, because you don't even think about that, but like that is the huge sell with a lot of the power tools is the battery life and the longevity of that. So that jump for you, that does make a lot of sense. So you were working in Las Vegas for a little bit, and where'd you go from there?
Yeah, so Las Vegas was really a market that I was just using to research the next generation power tools, and then I came back to Baltimore, which is where Black & Decker's headquarters was.
Okay.
And we started developing the next line of power tools, and it was an interesting program that Black & Decker ran at the time. It was called the Swarm Team, where they would send swarms of marketing folks out into the different markets to talk to end users, ultimately turning into sales. But the engineering teams would leverage the swarm teams by joining them to figure out what was next, and then coming back to headquarters to design what was next. So for the next 3-4 years, I developed different types of corded power tools.
Okay.
So I really wasn't in batteries at that time.
Gotcha.
I was just looking at different types of corded woodworking tools, sanders, cut saws that we could develop for the next generation. And I ended up designing the last project that I designed at Black & Decker was a belt sander that was used by cabinet shops at the time.
Okay.
And then after that, I was recruited by Bose to come up to Boston, which is where Bose's headquarters is, just outside of Boston.
And this is like Bose speakers.
You got it, yeah.
Okay.
And I know you've mentioned in some of your other podcasts, Bose has come up as a speaker, but it's really an amazing company. It's very different than Black & Decker, where Black & Decker was a very catalog-focused company. It was where are the holes in our catalogs for power tools, and what's the next tool that we need to develop to fill that hole.
Yeah.
Bose was very opposite. It was very technology-driven. It was, okay, what are the amazing technologies that we can develop in acoustics, and then what are some products that we can put out that use those technologies? And you may know the noise cancellation headsets that Bose put out.
Yeah.
That was a technology that they developed in the early 90s, and they weren't really sure how it was going to be commercialized. It turns out that airline pilots, it was very popular with airline pilots, and so one of the first products that they used that noise cancellation technology in were the two-way communications that pilots wear. And they were great. That wasn't super lucrative because they're just not,
as many that you would actually need.
That's right. That's right. So when they then launched the kind of the consumer version of that, which was kind of the one-way noise canceling headset, it took off. Yeah. And it really changed the game for Bose. So that's a great example of some technology that they developed and then found a product for. They also they developed some really efficient ways to package acoustics so that you get really big sound out of very, very small enclosures. Yeah. Because acoustics, they tend to the more performance that an acoustic box has, it really has to move a lot more air. And so usually the bigger, the louder. And what Bose developed were really efficient models of waveguides and kind of mass spring models of transmission lines where they could create big sounds out of small boxes. And that's really what Bose was known for, back in the day, were these speakers that were small but had massive sounds. And and so we developed. I joined Bose, and we developed a number of these kind of amazing products from these technologies. And one of the areas that Bose was headed in was getting into automotive suspension systems, which was way off brand for them. They were doing a lot of work with General Motors and putting speakers into cars. But one of the really cool technologies that they had developed was this active suspension system, which was basically a speaker that was kind of controlled in reverse. So instead of broadcasting sound out of the speaker would be tied to your suspension system. It would read the road, and then it would adjust your suspension as you went over bumps so that you would completely eliminate all the roughness of the road. And so you could drive over.
That's crazy.
It's amazing. It's amazing technology, and it would so you could hit speed bumps, and the car would pick up the tire over the speed bump as it went over it. You wouldn't even feel the speed bump. So these active suspension systems, they ended up commercializing in different forms. But one was an active suspension system actually for a truck's like a long range truck's driver's seat. So a truck driver sits in the seat and gets pummeled by the road as they drive cross country. And what Bose developed was essentially a suspension system for the seat that allowed the driver to basically erase the road noise from their back and their and their body.
That's crazy.
It's amazing. So another example of where Bose took a technology that they had developed and then found a product, a new application. One of the last products that I developed at Bose was the Apple Sound Dock, which housed an iPod. If you remember back then, iPods, and iPods had hard disks at that time. This was in the early 2000s, where the drive was actually spinning, and so you would. It wasn't solid state at the time. If you were saving all of your songs on an iPod, it was going onto a disc that was spinning. And so when you put that iPod in front of
a physical disc inside the iPod.
Yes, a physical hard drive.
Okay.
So if you put that iPod on in front of a speaker, which we did, so that you could play your songs to the room, that speaker, if it played loud, would skip the drive. And so we had to build a suspension system around that disk drive that would protect the iPod. Anyway, it was a super successful product. And
when you say building a suspension system, what does that look like? What does that entail?
Yeah, a suspension system is basically just a kind of a bandpass filter where, in mechanical terms, it prevents vibrations from making it to the sensitive piece of hardware.
Okay.
So if you're sending vibrations out through the world, into the world from a speaker, and they're potentially going to hit your disk drive, you want to isolate that disk drive from those sounds and those vibrations so that it doesn't skip.
And this was the same thing they were doing with the vehicles, with the truck drivers' seat suspension and things.
Very similar, only that was an active suspension, so that would be very. It would listen to the road and it would adjust.
Okay.
This was a passive suspension, so it was more like just putting it on a nice pillow.
Yeah.
That would prevent vibrations from getting to the hard drive. But anyway, yeah. So that's about that point is when Black & Decker came back calling, and they said, "Hey, we know you're up in Boston. We've discovered a battery technology that we'd really like to get to know better." Coming out of MIT, it was called A123 Systems, and this was a new type of lithium-ion battery in the early 2000s. And they said, "Hey, we're working with this small company, A123 Systems. They're all a bunch of very smart material scientists and chemists, but none of them have mechanical engineering expertise on how to package their battery into a product." And so they introduced me to the company, and I got to know the founders and ended up joining them.
So you went back to Black & Decker.
So no, Black & Decker steered me towards A123 Systems.
Gotcha.
And then all of a sudden I was back working.
Made that connection.
Yeah, working with Black & Decker and their battery experts, but from the battery side.
Gotcha. Okay. Did you ever think that you would have ended up there? Did it feel kind of
No.
random or?
So totally random, because as a mechanical engineer, I chose Black & Decker because of the moving parts and the motors and the gears and the tools. And Bose was kind of a step away from moving parts, but there was still vibration and there were still mechanical systems. Going into batteries, there's no moving parts.
Yeah.
Right. A battery is an electrochemical system.
Yeah, that's more chemical rather than mechanical anything. Really.
That's what I thought. And so I was very skeptical going in, but it turns out that mechanical engineers are really the center nucleus of any product, any hardware product, even a battery, where you take the constraints from the kind of the engineers, the experts of the internals. At Bose, that expert was an acoustics engineer.
Yeah.
So if you're
that's an actual title, an acoustics engineer.
Absolutely.
That's awesome. I didn't know that.
And Bose has some amazing acoustics engineers.
Yeah.
And they would teach you as a mechanical engineer what was important about the acoustics of a mechanical enclosure. And then the mechanical engineer would basically package the acoustics along with the electronics into a product. So if you look at a wave radio is just a bunch of electronics packaged with acoustics so that you can, you have a speaker.
Yeah.
And in the battery world, it's very similar, where you have experts in chemistry and material science who basically define how a battery works and tell and teach the mechanical engineering team what is important about a battery. And then the mechanical engineering team packages the chemistry.
Yeah.
So the electrochemistry, the electrical components into what's essentially a battery cell. So you can think of it as what you buy at the grocery store, an A, B, or D battery. That cell is a mechanical packaged system that is housing an electrochemical system inside of it.
That is one thing. Batteries added to the list of things that I use every single day. Couldn't tell you how they worked. Genuinely. Along with cameras, that's added to the list of things that I just don't understand. But describing it more as a cell where mechanical and chemical engineering come together and work perfectly in sync to make this thing work just makes complete sense. But obviously the batteries that you were working on were probably much more different than the batteries that we see, on the shelves at the store. So what kind of projects were you working on when you first kind of stepped into this new role with you said A123?
Yes.
Okay.
A123 Systems. This was a company was born out of MIT, was born out of the material science labs. And what was special about this type of lithium-ion chemistry was that it had a much safer and more powerful round-trip kind of efficiency. So these are all rechargeable batteries. So when you charge or you discharge the batteries, you're using up its life. And so you can only charge or discharge batteries for so long before their capacity depletes, right? So it's just like we see in electric vehicles today. You buy a car and it has 400 miles of range, and then you drive it for 5 years, and then all of a sudden it has 300 miles of range.
Okay.
You wonder what happened.
On a full charge, you mean, for that range?
That's right, on a full charge. So as you pull the car off the lot, and for the first year you're charging and discharging it, and you get on average, 400 miles. If you then revisit that 5 or 6 years later after you've driven it for a long time, or even if you haven't, it's just the battery's aging, you get less. And that just is the natural
life cycle of batteries. Yeah.
That's right. So what A123 Systems developed was a new type of lithium-ion battery that had better life than traditional lithium-ion batteries. And at the time, lithium-ion batteries hadn't been around for that long.
Yeah.
Right? It was in the early 90s. That I think Sony was the first to bring out lithium-ion batteries, and they had a certain chemistry that they used, which was a cobalt oxide type of battery. Anyway, A123 Systems developed a phosphate battery that had better life, had more power, and was safer. And by safety, I mean like literally explosion.
Yes.
So we know like lithium ion batteries in your phones can explode. And that still is the case. But one of the reasons why lithium ion motor batteries can explode is because when they are abused, the chemistry inside of the battery releases the different parts of the chemistry. And in traditional cobalt oxide batteries, one of the parts is oxygen. So if you're releasing oxygen at the same time as you're abusing the battery, and you have a fire, that oxygen fuels the fire, and it has
creates an explosion.
That's right, and it's this runaway effect of
which is why we can't usually have them, or they're so strict about those going on airplanes. Because I feel like that's every time I fly, that's like the number one thing they're asking you, and you have to click through I have no lithium ion batteries like in my checked bag, and honestly, in my mind, because I've been flying a lot lately, I'm like, do you think I know what a lithium ion battery is?
Oh gosh, you're probably not alone. But it's a simple way to think about it is that a lithium ion battery is just a storage tank of energy, right? So when you charge it up, it now has this huge amount of energy stored on it. And if you abuse it, let's say you crush it, or it gets penetrated by a nail or something, shorts it out, all of that energy is going to be released very quickly.
Yes.
And that is heat. That turns into heat. And if that heat is fed by another fuel, oxygen, which is released in traditional lithium-ion batteries, then that can turn into a major explosion and a runaway and a huge fire. And that's what does happen, especially the fires that we see in vehicles. But what A123 developed was a chemistry that was very powerful, had a lot of energy storage, and could deliver that energy quickly, but did not create oxygen when it was abused.
Okay.
And so, yes, the batteries, when they shorted, would get very, very hot, but they wouldn't go into what we call thermal runaway.
An explosion.
And an explosion.
Okay.
Exactly. So you asked about different applications. This was in the very early history of lithium-ion batteries. And power tools, when you go shopping at Home Depot or Lowe's, most power tools, they are using lithium-ion batteries right now. But that was not the case in the late 90s or the early 2000s. Lithium-ion power tools would use either a NiCad, nickel cadmium, or a nickel metal hydride battery, which are they're a simpler chemistry, a safer chemistry, but they don't have the types of capacity that a lithium-ion battery has. So they were going through power tools were going through the same evolution that cell phones went through in the 90s.
Yeah.
If you remember, old cell phones had huge batteries. Back then, they were the same types of batteries. They were either NiCad or nickel metal hydride, and they moved into lithium ion to get more capacity in a smaller package.
Yes.
And that's exactly what power tools wanted to do. You wanted your drill to be more powerful but lighter weight.
Yeah.
So Black & Decker wanted to develop a lithium-ion battery for their line of power tools, and so that's what we were working on. That was our very first product.
Were they the first company, in power tools at least, doing this?
They were, and when they launched it, a number of other companies, their competitors, did the same thing.
Of course.
Yep. But one of the reasons why they were attracted to A123 Systems is because the batteries were so much safer. And when you have a power tool battery charging in a house or in a building, and something
in a
goes
wood
wrong,
structure that they're in the middle of building, and you're gone for the night or something, you don't want it exploding.
and that is a huge potential. It's a huge risk. So they approached this from a very conservative perspective and said, we're not going to integrate lithium-ion batteries into our tools until we understand the safety of them, and so we want to be very conservative and safe about this, and so they were very interested in that.
Yeah.
And they were our big first customer, but very quickly, electric vehicles took on that same attitude and approach. This was, remember, early 2000s. This is when Tesla first emerged. Back then, this is when Toyota was offering the Prius, which was a kind of a hybrid, hybrid vehicle, and the Prius actually was using these nickel metal hydride batteries, old technology, and what they wanted to move to were more energy dense, more powerful batteries.
Because that was, I would imagine for a vehicle, that's not a great option if the longevity is not there, and even just like how long it can go without charge. I mean, like, how frequently would you be charging these vehicles if it was like your everyday car?
You're exactly right. And so this is what they were facing. The Prius of 2004 had a trunk full of battery that could take them 5 or 6 miles down the road. Right?
Really?
This was a hybrid.
So it was just not efficient, like at all.
Well, back then it was doing its job. It was a hybrid, right?
Yeah.
So it would charge when you brake at a stoplight, and then it would give you an assist out of that stoplight. But when you were running on the highway, you were running on a gas engine.
Gotcha. Okay.
Right. So this was a kind of a charge discharge hybrid vehicle, and it wasn't meant to go for a long period of time on a battery.
Okay.
More than a mile or two, and it would run out. So eventually, Toyota launched a next version of that hybrid called the plug-in hybrid, which instead of 5 miles became 50 miles. So now you could plug in the vehicle at home, and you could charge up 50 miles worth of charge, and then you could drive to work and back. But if you went any further than that, you used the IC engine inside of the vehicle, the gasoline engine.
Yeah.
And to do that, to go from a trunk full of batteries that took you 5 miles to a trunk full of batteries that took you 50 miles, they had to move to lithium-ion batteries, which they did. And they were working with Panasonic when they did that. But there were other companies like Tesla who wanted to launch an all-electric vehicle.
Yeah.
They weren't looking at
no
hybrids,
gas engine, anything.
No gas engine, not a hybrid, not a plug-in hybrid, but a fully electric vehicle. And so they needed a whole chassis full of batteries, which is ultimately what they did and still is today. The entire chassis is a battery pack. And they needed lithium-ion batteries to make that work. And it was so early on, and there was so much unknown about the abuse of batteries in vehicles and crash testing and everything like that, that they were taking a conservative approach as well. They wanted to use a lithium phosphate battery instead of a lithium oxide battery for the same reasons.
Gotcha.
They ultimately ended up not using A123 batteries, but A123 at that time saw the opportunity of getting into automotive as not just providing batteries to power tools, but to a much broader, bigger industry. The automotive industry, which is emerging, and at that time, General Motors was looking at how they could compete with Toyota and ultimately Tesla, and they were launching the Chevy Volt.
Which was that their first electric vehicle, or at least shot at it?
Well, at that time in the 2000s, yes. But there's a great documentary on the EV1, the General Motors EV1, which was the first electric vehicle that was launched in the 90s. Great story. We won't get into that because that was way before my time in electric cars. But there was that was their first electric vehicle, the EV1, and that was essentially killed by the oil and gas industry. But we'll leave that for another discussion at another time. So this was when everyone came back to electric vehicles, and new companies were being born, like Fisker Automotive. Fisker was making its own version of the plug-in hybrid, and A123 Systems partnered with Fisker to build batteries for them, and was partnering with General Motors to build batteries for them. We ended up going public in 2009 to expand our factories in Detroit. So we actually built these huge battery factories in Detroit as well as in outside of Shanghai, China.
Okay.
So we were making a lot of batteries at that time. But what was also emerging at that time was this new regulations in motorsport, specifically Formula One. So one of the things that Formula One does really well is it follows the trends of the industry.
Okay.
So Formula One is governed by the FIA. The FIA is the body that writes the rules for Formula One.
Okay.
It's like any other racing series, like NASCAR, where if you're going to compete in Formula One, there's a whole rule book on how you can design your Formula One car.
Okay.
Right? It talks about how large it can be and
the do's
the
and
weight.
don'ts and
Exactly, what you can do, what you can't do, what's required, what's not required. So in 2006, the FIA released a new regulation that would go into effect in 2009. So it gave all the teams 3 years to develop, that basically said Formula One cars can go hybrid if you want to. This was the first time that in motorsport that, that
any
hybrids,
motorsports, like even NASCAR, anything else, like were they the first ones doing this?
I think so, yes.
Okay.
Drag racing was starting to go electric, maybe not hybrid, but was starting to go electric, and that's a whole nother story. But we at A123 Systems, one of the first motorsports that we supported was drag racing, and we would put our batteries onto an electric motorcycle that immediately started breaking records. So that's one of the things that you can. One of the things you find out very quickly as you get into electric cars is that they perform very differently than gas cars, right?
Yeah.
So you can get in a Tesla that's not a super high performance vehicle, but it still accelerates like a Porsche.
Yeah.
0 to 60 in like 3 seconds. It's unheard of, for gas engine cars. And the same thing was true for drag racing. So this was one of the kind of the low hanging fruit of the industry where we could show off our technology, because you could put these batteries on a bike, an electric motorcycle, and it could go from 0 to 60 in less than 1 second. And it would do a quarter mile.
That's ridiculous.
Yes. And the bike that we worked with was called the Kilocycle. It's something that you can look up later, but the Kilocycle, like kilovolt, but the Kilocycle immediately started competing with the fastest drag racing bikes in the world, the top fuel bikes. And it was right around that same time that the FIA changed the regulations for 2009. And so we started to work with the Formula One teams because they had this opportunity to go hybrid that they wanted to take advantage of.
Yeah.
But they didn't know anything about batteries. So they started to talk to all the battery companies in the world, and we started to talk to all the Formula One teams in the world. And it was
kind of like partnership.
Yes, exactly. That's what they were looking for, because the Formula One teams are always looking for an edge.
Yeah.
And what they don't want is the same technology that everyone else has.
Yeah.
So they want to lock you down.
And a quick side note on that. So if you said it's the FIA, is that correct?
FIA, yeah.
If they say like, here's the parameters, here's like the rule books, this is what you can do, this is what you can't do. Is there a lot of wiggle room for like creativity in coming up with something? Or is it like pretty close that like everyone does end up with something pretty much the same, but with very minor tweaks like here and there?
Yeah, so that is a great question. And the short answer to that is that the teams who cheat the best and go around the rules the best are the ones that win.
Yeah.
And
that's probably true for a lot of different things.
Yes. But it's easier to cheat and bend the rules like you're describing when new rules come out for the very first time. So what tends to happen in motorsports is that the rules will evolve over the course of 20 or 30 years.
Yeah.
And by the time, you're at the end of this evolution, it's pretty homologated. So everyone is pretty much on the same page.
Yeah.
And that's kind of where we were in 2006, 2007. All of the cars were very closely designed. There were some aerodynamics differences between them, where teams were really stretching the rules, and then the FIA would step in the next year and outlaw what the teams did to cheat.
So then you end up kind of all being pretty close to the same.
Pretty close to the same. So what happened in 2006 is they introduced this new rule of hybrid, battery technology into Formula One, and that opened up this new age of Formula One racing.
Because that's like a huge opportunity. That's like not just like a little thing. They're like, oh, you can do this now. I mean, that like opens up an entire new thing to test.
Totally. Yeah, it's a whole new area for engineers to dive into and to understand and to optimize. And it took a number of years for the teams to fully optimize. But yes, it also represented, like you said, an area to differentiate between the different vehicles. So not everyone was using the same battery technology or the same motor technology. They all did their own thing. And so when the very first race in 2009 with different battery technologies. There was a whole lot of difference between all the different teams because of that. Everyone was doing their own thing. But in 2006, 2007, as we were interviewing the different Formula One teams who were looking to get into batteries, it became very clear that McLaren and Mercedes, who were working together, were the most kind of sophisticated and interested.
Cutting edge and
really taking the new regulations seriously, because you had this motorsport history that never included batteries or hybrids.
Mm-hmm.
It was just make the car louder, put more cylinders on the car, more horsepower. And now you're saying, okay, actually we want to be more conservative. We want to be able to recover energy in these batteries. We want to have better round trip efficiency. And a number of the teams in 2006, 2007 thought that the FIA was just kind of doing this on a whim and didn't take it seriously. They said, oh, this battery hybrid stuff won't be around much longer. It's only, it's just a fleeting idea. And so we're not going to invest in it because in 3-4 years from now, the FIA is going to change the rules back and hybrids won't be. It turned out to be a mistake.
Yeah.
But a number of the teams thought that way. But McLaren and Mercedes didn't. They knew
that this is where it was going.
Absolutely. And the FAA does a really good job of this kind of trickle down, where you develop the technology on the racetrack and then it trickles down into the road car. And this is what Mercedes loved. And they do this all the time with their motorsports, is that they develop these really amazing technologies on the racetrack for their race cars, but then they move them down into their S-Class or their E-Class or their other road cars eventually. And so they saw hybrid battery technology as one of those technologies that they could go really press on.
This will trickle down
This will
eventually.
trickle down, yeah. So they took it very seriously. And of course, we're a battery company. We needed someone who would take this very seriously. So we partnered with Mercedes to develop a battery pack for Formula One. And one of the reasons why they wanted to use our batteries is because of that safety.
Yeah.
So not only were they
don't want
high
anyone
performance,
exploding on the road. That's not a good look.
These cars can crash at extremely high speeds and then go flying everywhere. And you couldn't have this battery pack add to the danger. And it sits right underneath of the driver in the kind of the crash protection zone. So if something bad happens, the driver's at risk. Yeah. So they really liked the A123 chemistry. They just needed a cell that was designed for the Formula One circuit. In other words, it had to be even higher power. It had to be kind of the most high power lithium-ion battery in the world in order to perform on the circuit and make the car go faster. Because you had to put this battery on the car that weighed more, right? The battery was heavy, so it had to add more horsepower than it did add kilograms.
Yeah, weight.
And it had to do that compared to an internal combustion engine. So you had these really efficient Formula One, IC engines that were made out of aluminum and extremely high horsepower to weight ratios. And now we had to develop a battery
that did the same thing.
That it was even better. Yeah, it was even had a higher power to weight ratio. So we did. So we worked with Mercedes to develop that Formula One battery, and then launched it with them in 2009, and they raced with it until 2014, and were very successful.
Yeah.
And then the regulations in 2014 changed again. The FIA liked the battery hybrid model in Formula One, and they expanded on it. And they said, okay, we're going to now allow the teams to build bigger hybrid batteries.
Nice.
And we're allowing them to harvest energy not just from the rear tires, like through braking, but also through a turbocharger. So they introduced a turbocharger to the engine, and you could actually run the turbo fan with exhaust and charge the battery just with exhaust.
Yeah. So what is that? What is the science there with the turbocharger? What is that doing?
So the turbocharger takes the gases that come out of the engine, which are hot and expanded, and are coming out very, very fast, and a turbo will capture energy out of those gases by spinning a fan. So those gases come out and they spin a turbine. That turbine is then attached to another turbine, a compressor, on the intake of the engine. And so the exhausts are blowing through a fan that spins a compressor on the intake, and now you're putting more oxygen into the engine thanks to the exhaust coming out the other end. So a turbo has this ability to kind of supercharge an engine this way, but it only works when the exhaust is blowing.
Yeah.
So your engine has to be running at a very, very high speed in order to create that exhaust that you can then recover and put into the compressor in the front. What the FAA allowed now was you could put an electric motor on that turbofan. And so you could, even when the exhaust was not blowing,
the turbo was still
you could
going.
still run the compressor with this electric motor. And then if you didn't need to use the compressor, you could still blow the exhaust through the turbofan and use the energy from the exhaust to charge the battery through that electric motor. So that motor was, if you run a motor backwards, it becomes a charger. And that's the way that electric vehicles work. You know how you step on the brakes in an electric vehicle, it runs the motor in reverse, or wires the motor in reverse, so that your energy, the momentum of the vehicle slowing, is charging the battery pack.
Okay.
And that's how you recover energy off of the
normal
off the road.
driving patterns.
That's right, exactly. If you brake if you brake from a very high speed to a very low speed, the momentum in the vehicle is then turned into energy that goes back into the battery pack. And that's the way that Formula One operated from 2009 to 2014, where if you dove into a turn and broke the car very hard, you were charging the battery through the rear wheels. You were putting a large amount of that momentum from the vehicle back into the battery.
Yeah.
Which you still had from 2014 on, only they introduced the turbofan as well. So this was a second way that you could recover and use the energy.
Just a lot more efficient. And just kind of everything was working in tandem for the highest use of the vehicle.
That's right. That was the idea. The FIA wanted the vehicles to get more and more and more efficient, which they did. So all of a sudden you had energy sloshing around the vehicle from the rear wheels into the battery pack, into the turbofan, back out of the exhaust, back into the battery. It was this very complicated
like ecosystem almost.
Yes, on board. And it became this extremely advanced and efficient system of an opportunity for the teams that really executed it well to get a huge advantage. And at that time, in 2014 and 15, when vehicles were running on this system, if the system failed, the cars would lose 4 to 5 seconds per lap, which is an eternity.
Yeah, that's a lot.
You can't compete. Yeah, you can't compete without it. So it became an essential part of the drivetrain of Formula One. And this was back in Mercedes' heyday. This is when Mercedes was dominating the field. So Lewis Hamilton, their driver, was running this battery system as part of his powertrain in his Mercedes Formula One car, and was winning 7 championships at this time. And so we like to think that the batteries has a little something to do with it back then.
That's awesome. So how involved were you with being in the field? Like, did you get to be at a lot of these races, like in person, or were you doing a lot more of the back end work, or did you get to be like out there with them?
Yeah, so it was a transition. It was both. It was first in the lab developing the batteries. Second, working with the teams to integrate the batteries into the vehicles and the controls systems that went into the car, controlling and strategizing when it would use the energy, when it would pick up the energy on the track, and then thirdly, working with the track engineers and the drivers on when and how to care and feed for these batteries. So just like any other critical component of a vehicle, you needed to know how to determine whether it was in a good shape or it was in a bad shape. Like, was it about to break or was it healthy? And you would monitor it the entire race through.
Okay.
You could at this time you could replace the batteries and the components if they broke, but you had to do it after the race. And so during the race, you wanted to make sure that the battery was healthy. And so a large part of my job at that time was to work with the teams, the on-track teams and the drivers, to understand and monitor the batteries to make sure that they were healthy
How are you
during the
doing
race.
that monitoring?
So you build sensors into the battery pack. You watch their voltage as the voltage sags or as the voltage grows. So as you discharge the battery, the voltage will drop. And as you charge the battery, the voltage will increase. And you can tell a lot about a battery's health based upon that voltage change, which is the impedance, the resistance of the battery. And so we instrument up the batteries during the race, and you have all of this telemetry coming from the car into the garage. And you basically are watching a screen of
all different things.
Signals, all these signals coming in and all these battery voltages. And so there was this time period in which everyone was getting up to speed on, what a battery was, how to care and feed for it, how to keep it healthy, and then how to monitor it. And so that was a couple year time period. But then once the teams became experts, then they didn't need you anymore. Then they were their own experts. And
gotcha.
And so they still today are running these same batteries.
And like these same systems and everything. It's probably like evolved a little bit from there, but
yes.
these same things that were placed almost 20 years ago, I guess, are all still being enacted today.
That's right. And there's a new regulation coming out in 2026, which is really exciting, where they're starting to evolve this system even further. Now in Formula One, they want to incentivize teams to develop more efficient powertrains. And if you do, if your powertrain is more efficient, in other words, if you can get around the track in using less energy than other cars, then you get a bonus, and that bonus is that you can use that energy later throughout the race. And this is amazing for electric vehicle powertrains because it's pushing efficiency, it's pushing energy efficiency on the track, which will then trickle down into our vehicles. Yeah,
do we still see that happen a lot, that so much of it starts with Formula One and then still trickles down? Like, does that still occur to this day?
It does. It's not everything. It's a small percentage. It's probably 10 or 20% of the technologies that are developed on the track actually make it into the road car.
Yeah.
Maybe even less. But yes, that's the idea, and that's why big brand names participate in motorsports.
Because you just learn so much at that rate of speed. You kind of have to do so much research and experimentation.
You do, and it's real and it's perceived. So there's the brands like Mercedes will race, develop their technology, and then talk about it and say, if you watch this Formula One car go around the track, that same technology can be yours in this S-Class, vehicle or whatever if you buy it at the dealership, which is not really the case, right?
Yeah.
It's not. It's a little bit of embellishment. It's a lot of embellishment. But Mercedes, the marketing teams at Mercedes have done an amazing research to the point where they can track sales at dealerships based upon how long or how much their logo is on display during a Formula One race. So if the car is winning, then the Mercedes symbol is shown on screen.
And that's pushing sales all the way down to the people like you and me.
That's right. And that pushes sales.
Wow.
They've showed, very strong correlation between that. How many seconds are on the TV versus car sales. And
those are things like someone like me, I would never think about that. If I walk in and my dad's watching a Formula One race, I would never be like, oh, that right there is marketing in and of itself.
It's
to the nth degree.
Incredible marketing.
Wow.
Yeah, it really is. It really is.
But definitely not cheap what they're doing. I don't doubt that is probably a very expensive experiment to be in.
Yes. But the Formula One industry and motorsports was a huge win for A123 Systems. In fact, we took that battery that went into Formula One and we brought it into endurance racing. So just like, there's other classes like NASCAR, Formula One, there's also the WEC, which is the World Endurance Championship, and that's best known for the 24 hours of Le Mans. The racing, the really long races. So Formula One races are normally about an hour. But WEC races are, 3 hours, 6 hours, 12 hours, 24 hours. So the totally different race, totally different duty cycle for these batteries. But what happened was that Porsche saw what we were doing with Mercedes and approached us and said, we are getting back into WEC, endurance racing, and we want a very powerful hybrid battery and powertrain. And so will you develop with us what you developed for Mercedes? And we did. And so this was in the, kind of the 2011, 12, 13 timeframe. And in 2014, we started running with Porsche. And sure enough, Porsche, won the world championship, won Le Mans, and the world championship for 3 years using our batteries too. So this was all a great win in motorsports. It was a very good fit. These batteries were a very good fit for motorsports. But what was happening at the same time is that the electric vehicle industry in Detroit was just trying to get started. And
you mean like for the regular like road cars?
For regular road cars. So this was more than 10 years ago, right? This was 2010, 11, 12. We were making a huge investment in battery manufacturing in Detroit, and General Motors and Ford and Chrysler, everyone was, had their electric vehicles on their roadmap, but none were released, and there was not a huge demand for batteries. So what happened was there was this imbalance between supply, the battery factories that we built in Detroit, and demand, the electric vehicles coming online. And ultimately, we were a few years ahead. And because we were a small startup company that had just gone public, we ended up running out of money. And so A123 Systems went bankrupt around the 2013 timeframe and was purchased by a large automotive supply company in China. And so this great chemistry, this great technology that came out of MIT labs and then, had all this promise is now today part of a large Chinese company that's producing these batteries for electric buses in China. It's a very successful company, but it's an example of a kind of a homegrown U.S. technology that we lost.
Yeah.
That we couldn't
just because it was just a little bit too early.
Yes.
At least with automotive, maybe they were behind. I don't know what comes first, the chicken or the egg. Like if you guys were too ahead or they were too behind, but just barely like missed each other.
That's right. It's all about timing.
Yeah, of course.
It's all about timing. So it was right around that time, 2014, that the company was sold and a number of us left, and so that's when I went off and formed Desktop Metal.
Desktop Metal. So let's get into Desktop Metal a little bit. So you are the co-founder and the CTO. So tell me a little bit about like the origins. Like how did this come about? Who were you working with at the time that you guys came up with this idea?
Yeah. So my co-founder and I, we'd been working together at A123 Systems for a number of years, and he went into investing into venture capital after the kind of the downfall of A123 Systems, and he wrote a thesis on advanced manufacturing, and that thesis included all different types of hardware and software that were going to be necessary for next generation of kind of advanced manufacturing technologies. And it included CAD software companies and also 3D printing companies. So he started a number of 3D printing companies, as well as some software companies that supported advanced manufacturing, as well as some marketplaces and some manufacturing companies that actually produced parts. So his thesis was coming together very nicely, but there was one piece of it that was missing, and that was that metal additive manufacturing or 3D printing of metal parts needed to get easier, more accessible, and less expensive in order to grow to critical mass and economies of scale. Because metal 3D printing had been around for about a decade at that point.
Really?
Yep. And so metal 3D printing really was born in the late 90s, early 2000s with laser-based processes. So this is firing a laser into a bed of powder and melting a little voxel. Now, a voxel is like a pixel, on a screen.
Yeah.
A pixel is a two-dimensional, pixel that makes up an image. A voxel is a three-dimensional pixel that would make up a part, right? And so
That's crazy.
isn't it crazy? Yeah. So if it's back in the early 2000s, metal 3D printing really existed as a laser firing a small little dot into a powder bed and creating a voxel, and doing that over and over
Is
and
the
over
powder
thousands.
metal?
And the powder is metal. Yes.
Oh, okay.
So the powdered metallurgy has existed for over 100 years. So there's a whole industry of making parts out of powdered metallurgy that has evolved since the early 1900s. And the way that you manufacture that powder is different, but essentially you create three-dimensional parts by taking powder and sticking it all together one way or another.
Yeah.
And the most traditional way to do that is just by putting it into a die and compressing it. Right. So if you fill a metal pocket that's the shape of the part that you want, let's say it's like a washer, and then you compress it, the metal powder, really hard. The metal powder will stick together, it'll compress, and then you can take that part out. It's called a green part. And then you put that green part into a furnace and you do what's called sintering. Sintering takes the metal up to a temperature that's just below its melting temperature, but a temperature at which it becomes very sinter active, which means that the atoms can actually migrate from high energy states to lower energy states. So if you have two particles of metal, it's just like two drops of water. When they come together, like two drops of water, when they come together, they touch and they turn into one big drop of water. That is a reduction in surface area. So if you have two drops, it has a lot more surface area per the mass than a lot more surface area than the volume, per mass than it does when it's together. So when you have two metal particles touching, or lots of metal particles touching, there's a lot of surface area there.
Yeah.
So it's in a high energy state. And what sintering does is it brings the metal up to a point in which the atoms are very active and can jump around, and can take that high energy state, which is lots of surface area, and reduce it to a low energy state, which is a lot less surface area. And so essentially what it does is it takes the porosity that's in this green part and it drives the porosity out. And as the part shrinks, and you essentially, just like the two water droplets touching that turn into one big water droplet.
Is it fusing together essentially?
It is chemically fusing together.
Gotcha.
And in sintering, the grains of metal, right? The grains that form in these crystalline metal structures grow bigger than the original particles of metal themselves. So you're erasing the history that the part was even started as powder. So this has been around for hundreds of years. Sintering has been around for a long time, right? Just taking powder and forming parts out of it. And it evolved in the 60s into metal injection molding. So metal injection molding is basically the same thing. But instead of taking powder and compressing it into the shape you want and then sintering it, you're taking that same powder, you're mixing it with plastic or wax, and then you're injection molding it into a die just like you would a plastic part.
Yeah.
Right? So just like you would make a plastic piece, you take this waxy material that's full of metal powder and you injection mold it into the same cavity, and then you take that cavity out, you remove the wax and you sinter it, and it becomes a fully dense metal part. So metal injection molding was this kind of amazing step up in complexity, that you could move powder from this raw material into a very complicated shape. And then what happened in the late 90s, early 2000s is 3D printing took on and said, okay, we're going to use the same metal powder that we've been using all along, but we're essentially going to weld it up into the final shape. So you would spread the powder, and the powder is very, very fine. It's almost like flour. So if you were to touch it, it would puff up in the air and float, because it's very, very fine particles.
Seems dangerous to work with.
Yeah, you definitely wear PPE and you be safe around it, and you try not to inhale it. But these machines were developed that controlled the atmosphere and controlled the powder from floating away, and lasers were fired into the powder to create essentially two-dimensional images, and then another layer of powder would be spread over top of it, and then another two-dimensional image would be created by firing a laser into that powder and creating these voxels. And the voxels above would fuse with the voxels below because they would melt, kind of downward. And eventually, after you did thousands of layers, you'd then have these parts that were built inside of these powder beds, right?
Yeah.
These big old, chambers full of powder, and then you'd empty the powder out that you didn't fire the laser into, and you would have this, your metal part would essentially be welded together, voxel by voxel, hundreds of thousands, millions of these little voxels just welded together. And you'd 3D print your part out of the same material that we'd been using for powdered metallurgy for the past 100 years.
And so, it was somewhat, because my understanding of 3D printers, like I was telling you, Shep's son has one and makes all fun little like toys and things, really cool stuff. And I mean, it's super interesting to see that even like just the fact that it's even like commercially available to people, but that it's, my understanding of it is that the ones that are plastic or like almost like a vinyl of some kind, it's layers just over and over, and it takes many hours to do it, but and you can change the like gauge of the plastic that's coming out, and it's kind of just creating like these layers over and over and over until you have like your, not image, but your toy or whatever it is that you made. So it's still similar to that, but it's coming out of this metal powder.
That's right. That's right. So you have what you're describing is the very traditional 3D printing that we as consumers can buy, right? And we can put it in our house. Kids use it in school and everything. And it's a great learning tool on how 3D printing works.
Absolutely.
But you're absolutely right. It's a simplified, what we call extrusion-based process. So you're putting in these filaments of plastic, and they get extruded out through a nozzle at a very specific size, and then that path is indexed around the part layer by layer by layer, and the part grows and is built by these traces of essentially the two-dimensional cross section of the part. So there's some similarities there with how we do metal printing, and actually the 3D printing industry has grown over the past 20 years to include so many different types of what we're describing, so many different strategies on how to 3D print a part. We talked about extrusion-based, we're talking about laser powder bed-based. Those are just two of maybe 13 or 14 different ways that a part could be 3D printed. And so we won't get into all of them, but the plastics industry has kind of grown up in its own way, and then the metals industry is growing up in its own way. Plastics 3D printing has been really around since the 80s, the 1980s, when a company called Stratasys was born, one of the first companies to 3D print plastic the way that you just described it. And it's grown to be a juggernaut, a huge company, and is very successful in providing 3D printed parts for all different types of industries, including Formula One. Formula One uses 3D printed plastic parts all the time on their aerodynamics and everything. So the metals industry, though, was a few decades later, started in the 2000s and was very laser-based. And then it grew up towards the industries that could afford it and needed it. And those were aerospace and medical. And because of that, the machines became very expensive, and they became very sensitive and difficult to run if you were just an engineer. So it wasn't like you and I could go buy a 3D printer right now and print plastic. Yeah. Back then it was, these were millions of dollars.
Really advanced.
And so getting back to, when we founded Desktop Metal, laser-based printing had been around for, at least a decade, and was evolving towards aerospace, like expensive industries that needed high precision parts. But if you were a mechanical engineer like I was, and I wanted to print metal parts in my facility, I didn't have access to that. It was very expensive. It was almost out of reach. Yeah. And so our thesis was that we needed to make metal 3D printing more accessible, easier, less expensive, so that it could be more widely adopted. And that's what we founded Desktop Metal around in 2015, is to fill this kind of this slot of needs within the advanced manufacturing, revolution that was happening back then.